The movement of the sun at the centre of our solar system sets the rhythms of life down here on Earth. Its rising and setting mark the beginning and ends of our days. Its presence or absence sets our seasons, and it provides the energy on which almost all life on Earth depends. Its presence is a constant in all of our lives, which is why it's remarkable that every 18 months or so, across a tiny slice of the planet's surface, the sun disappears, briefly, in a total solar eclipse. These events have been studied since ancient times with awe, wonder, and fear.
These awe-inspiring events have allowed people to observe the sun in ways they can't at any other time. They have revealed the secrets hidden in the bright light. In 1715, an eclipse over the UK, which was timed at multiple sites, gave us a better understanding of the moon's orbit and helped us predict future eclipses. And in 1919, 2 coordinated observations provided experimental evidence for Einstein's theory of general relativity.
It's no wonder we're so fascinated by eclipses. So tonight we're looking at technology which will allow us to create eclipses on demand, to study not just our own sun, but also the other stars across the universe. Welcome to the sky at night.
There's plenty of news from the universe this month. A team using ESA's Gaia satellite have discovered a black hole 30 times the mass of the Sun, lurking just 2,000 light years away. We haven't seen evidence for a black hole of this mass on its own before. And so the discovery marks a step forward in understanding how they're created. Closer to home, NASA's looking again at plans to bring back Mars rocks collected by the Perseverance rover. The original plans, despite ESA's help, were threatening to eat the entire planetary science budget and were unlikely to bear fruit until the 2040s. A review is looking for new ideas. If you have any, send them to JPL California ASAP. But in the meantime, Perseverance trundles on. But of course, the most exciting event for me personally last month was the total solar eclipse. I've been lucky enough to travel to 4 total eclipses in my time, and they're always incredible events. The one on April the 8th was no exception. And while I was in Ohio in America, Pete was more than 1,000 miles away in Texas. Both of us were in the narrow band of totality, where the moon blocks the sun completely, revealing its beautiful outer atmosphere, the corona. Well, that was the plan. And it's a beautiful morning. Very excited about what's coming up later and trying not to think about the fact that the weather forecast says that high cloud's going to roll in just when we don't want it to.
The skies, they're a bit mixed at the moment. There are lots of big blue patches up there.
Luckily, the temperature can change dramatically during an eclipse. In Ohio, it dropped by about 10 degrees. And that can change the wind, the weather, and the clouds. In the end, both Pete and I had beautifully clear skies. He got some amazing pictures. But pictures can't do such an event justice. They don't show the contrast between the detail in that pearly white corona, the purple sky and the darkness of the moon's disk. Nor do they really show the 360-degree sunrise, the orange as light seeps in all around us from beyond the shadow. And all the while, at the back of your head, there's just something screaming that the sun has disappeared. It's an incredible experience. Totality just passed. Every time I try and tell people what an eclipse is like, what a total eclipse is like, and there are no words for it. I cried. It was beautiful. There were prominences. There's a prominence, a bright orange glow at the bottom of the sun. Beautiful corona, long streamers, a solar maximum corona, all of which makes sense scientifically, but my God, we're so lucky to live on a planet that does this.
We made it. We got totality. The skies cleared and It's just an amazing sight. It's really, really emotional. It's been an emotional roller coaster. I never want to do another eclipse again. That's a lie, but it's absolutely superb. We saw the whole of totality. We saw Venus, we saw Jupiter. The corona was amazing.
Apart from the sheer magnificence of the event, eclipses allow us to study the sun in a way that we can't at any other time. When kids draw a yellow disk for the sun, or you look through eclipse glasses, you're seeing a layer called the photosphere. But rising above that, heated to over 1 million degrees, is the sun's upper atmosphere, the corona. And it's this region that scientists are able to study when the light from the sun's disk is blocked. But each eclipse lasts just a few minutes at most, so scientists have been thinking about creating their own controlled eclipses. Maggie's been finding out about a new mission that does just that.
I'm in Belgium, at a space facility where they're in the last stages of a very special mission. Wouldn't it be great if we could have a total solar eclipse every day? Well, that's just what the European Space Agency are trying to do with their new mission, Proba 3. This will involve 2 satellites flying together in formation. One acting like the moon during an eclipse, blocking out the light of the sun's central body, while the second will observe the sun's corona. By blocking out the sun in this way, Proba 3 will reveal the innermost workings of the sun's corona, allowing us to study it in more detail than ever before. This should hopefully give us better prediction and protection against space weather, but also reveal some of the greatest mysteries of our sun. I'm meeting Damien Gallino, project manager of Proba 3, to find out more. Now, you've been involved in Proba 3 right from the get-go. So where are we at the moment?
So closely, the 2 spacecraft are integrated. They are now in the clean room under testing. And it's the result of the work of more than a dozen of companies all over Europe. A long journey, never boring, every day is a new day.
So how does the spacecraft work?
We want to demonstrate formation flying, precise formation flying. That's the objective of the Proba 3 mission. So we fly 2 spacecraft. One we call the occulter spacecraft.
And so the occulter is the thing that's going to block out the majority of the sun?
Yes, so that's the moon. And that will cast a shadow. So imagine the sun somewhere there. This will cast a shadow. And the other spacecraft that we call the coronagraph spacecraft, because this spacecraft will accommodate the specialized telescope.
Okay.
So the coronagraph will be there, and we'll have to be positioned precisely in the center of the shadow that will be cast by the occulter at a distance of about 150 meters.
So you mentioned that the distance between the 2 spacecraft is 150 meters, and that is defined by the size of the occulter. Why the balance here?
So, on the principle, the larger the better. But a larger occulter would mean a larger spacecraft, more need in power. So that's an engineering trade-off.
Okay, yes.
So the larger the better, ideally the moon.
Yeah.
The size of the moon would have been the best occulter we have in nature.
Yes, but hard to launch.
Hard to launch, yes.
Proba 3 aims to study the corona for 6 hours in every 20-hour orbit. That's like images we see during an eclipse, but for 100 times longer than the fleeting glimpses we get from natural eclipses here on Earth, giving us a detailed look that may reveal a solar secret. So, with this system, we are going to actually get a much more detailed view of the corona, but the corona very, very close to the sun. And I believe there's a mystery there, because the surface of the sun seems to be cooler than part of the corona. That seems very counterintuitive.
Indeed, if you take a source of heat, as our coffee cup, if you have your hand away from the source of heat, it's colder.
Yes.
Of course. But the sun is different. So the temperature of the sun is approximately 6,000 degrees Celsius. But the corner of the sun goes to millions of degrees.
And with Prober 3, we'll be able to get to that boundary between the very edge of the sun and that sort of massive temperature rise. And so hopefully the mystery will be solved.
Yes, hopefully.
So Damien, thank you so much. It's been fascinating getting an understanding of how this challenging mission will work. And I'm looking forward to seeing it in the clean room.
Thank you.
Thank you. The satellite is being tested just along the corridor, so I have to take a look. I'm meeting Marie Beckman, who is the Satellite Operations Test Manager. But this is a delicate piece of space kit, so we have to don some clean room gear before we can get anywhere near it. So, Marie, we're in between the two satellites now.
Yes, we
which
are.
Which is very exciting to see them. So can you talk me around the chronograph?
Yes, of course. So, first of all, we have the actual camera there. That's like why we are doing it, kind of, to do the pictures of the corona. Yeah, that's the science behind the whole thing. That's what we can find there in the left. It actually has a little door.
What does that do?
Yeah, so the door is actually there to protect the instrument, because it's not possible to have the full sunlight onto the instrument. So we have to wait. We have to make sure that the other satellite is positioned perfectly in front of the door, like casting the shadow onto it. And only then we can open the door and take the pictures of the corona.
And that perfect positioning will be done by the two spacecraft communicating with each other.
The two brown ones, these are actually the antennas making sure that we can communicate. Well, not
between
we,
the satellites.
but that the satellites can communicate between each other.
Yes, and this is one of the interesting things. It's autonomous, so this isn't being controlled from Earth. They are speaking to each other, keeping their distance and doing all that remotely.
Literally everything has to happen remotely, like automatically.
Yes.
This is also why the testing has to be so extensively. We really want to see that the satellites are able to do it.
Yes.
Yeah, it will be very boring for us in the end, because it will be one command every week to give the satellite the week schedule, and that's it.
Marie takes me to the other satellite, the one that will block the sun, to show me how the formation flying will be achieved. Now, this is the occulto. So what have we got here?
All right. So here we have actually the actual things that will make it possible to do formation flying.
Okay, perfect.
The first thing they will do is activate their VBS, which stands for Visual Based Sensor.
Okay.
And this Visual Based Sensor has two cameras, the wide angle camera and the narrow angle camera. So we call it the WAC and the NAC.
Okay, yeah.
And the WAC is the one on the right.
Okay, yes.
Those are the wide angle cameras.
Right.
Whenever they are active, they will be looking like this with their wide angle camera for the other spacecraft.
Yes, and the flashing lights of the other spacecraft.
Exactly. Space is dark, so if there would be no lights, this satellite would not be able to. Yeah, exactly. And then he will switch to the narrow angle cameras.
Yes.
To go into the centimeter precision.
You've found each other on the wide, you've narrowed it down on the narrow.
Yes.
Okay, so then what happens?
And then we go into the laser part.
Yes.
So we were in centimeter now with the narrow angle camera, and we're going to millimeter precision because we activate the laser. And the laser is behind that like orange ring. So that's actually a bit the story here of how the formation will be acquired.
Yes. These are just a few of the instruments that make up the two satellites. And each part will need to be thoroughly tested before they're ready to launch. Marie, thank you so much for giving us a tour around your babies.
It was lovely.
Yes, and I guess there's a lot of testing to do, but yes, it's going to make sure that it will work when it gets out there in space.
Definitely. Me and my team, we will go for it.
So good luck with the testing. And yeah, we can't wait to see those first results coming through.
Me neither.
This project feels so revolutionary. I mean, it's got everything from precision formation flying, autonomous navigation, and also views of the sun like we've never seen it before. So I'm really hoping that this work will lead to the next generation of satellites that will explore our solar system and beyond. So I, for one, can't wait until it's launched.
But while we wait, other stars have stories to tell us too. Pete's off to find out more.
In October 2023, a research paper confirmed that two planets had collided. This was an incredible finding and the first time that the remnant of two planets colliding had been positively identified. But incredible though this discovery was, what was amazing for me was how the discovery came about. I am meeting Dr. Simon Locke and Dr. Zoe Leinhardt from the University of Bristol, and a whole team from across the world to find out more. Hello.
Hey.
Lovely to meet you all. Wow, that's a gallery of people. This gallery of people were all involved in identifying two planets colliding. And the story began when Michael Rizzo-Smith noticed something unusual happening to the brightness of a star.
And I was working for a team called the All Sky Automated Survey for Supernovae. And usually we're looking for these very bright events, but we also catch some events that change in the opposite direction where they get fainter. We noticed a dimming event, which was quite unusual.
Okay.
So not being an expert in that, I posted that to sort of a forum called the Astronomer's Telegram, telling people we saw this sort of interesting object with the hopes that someone would follow up with it.
The Astronomer's Telegram is a free online publication where the latest astronomical observations are quickly reported to a community of thousands of professional and amateur astronomers. And that caught the interest of Matt?
Hello, yes. So initially I thought it was going to be a big disk or a set of rings around a planet moving in front of the star.
But there was another key piece of information that came in, wasn't there, from R2?
Absolutely. A Finnish amateur astronomer called Arttu Zaino tweeted at me and said, hey, didn't your star get very bright in the NEOWISE survey? And I went, what? So it almost doubled in brightness in the infrared, but it happened about 900 days earlier, which is completely unexpected.
The bright flash of light over 2 years before the star started dimming led Matt to wonder if what they were seeing was caused by debris from a collision near the star.
Matt got in touch with Zoe and I and was like, what do you make of this? Could this be a collision? And the more we thought about it, I think the more convinced we were that we were looking at something that was very consistent with a collision.
Right. But they needed more data, and this is when amateur astronomers and their telescopes got to work.
I have a day job as an engineer, and I had been following this object.
Right.
But I build my own telescopes. I did try to take a spectrum, but my telescope isn't big enough.
Unable to get the data needed, Hamish reached out to Olivier, who along with 4 other amateur astronomers in France, remotely operate telescopes in Chile.
So when Hamish tell us that it will be good to take a spectrum of this target, the next night we take this spectrum, we send it to Matthew, and that's the beginning of the story for us.
The technical achievement that Olivier's group did in actually taking a spectrum during the dimming and their productivity, 10 to 15 spectra a night.
Incredible.
I get 1 or 2 a night.
That's amazing, utterly amazing. How many clear nights do you get throughout the year in Chile?
Oh, it's about 300 nights per year, I think, around.
So 300 nights of clear skies. So based in the UK, I think it's the other way round. We probably get 300 nights of cloudy skies. Because of the data Olivier and his team provided, work by all these people and more proved the dimming star was actually the result of debris from the 2 planets colliding and eclipsing the star. This has been an amazing project. What does it mean for you to have that amateur input?
This is something which happened almost purely because an amateur astronomer tweeted at us and said, hey, what's going on here? This looks like your star. And having this wonderful community of astronomers all around the globe is absolutely fantastic.
It's been an absolute privilege to meet you, and it's been heartwarming to hear how amateurs and pros have been working together to come up with this amazing discovery. So thank you very much, and goodbye.
Dimming starlight can reveal explosive secrets. But it's by blocking out starlight we hope to reveal planets like our own. Chris is off to find out more.
At the Sharmanka Kinetic Theatre in Glasgow, they use light and shadow to bring their creations to life.
These are quite impressive sculptures with so much detail.
Yeah, there's a few. I'm here to meet Professor Beth Biller from the University of Edinburgh to talk about how shadows that scientists create can help us find planets like our own.
Shall I have a look around?
Yeah, let's wander. Oh look, there's a telescope, nice bit of astronomy. Beth uses shadows to directly image exoplanets and has a shadowcaster of her own to explain how this can be done. So normally, when we think about exoplanets, we're used to hearing about discoveries via transits. How does that work?
Well, we have a demo here that shows exactly how we detect a planet via transit. So if this is our planet and we have the right alignment, when the planet passes between us and the star, it's going to dim just a tiny bit of the starlight. And we can look at the star, and if we see that dimming in the very characteristic shape of a transit, we know the planet is there.
And ideally, you'd see transit after transit after transit and be able to pick this up.
Yes, and they would, of course, happen exactly once each orbit.
But you can't do everything that way. Why not?
Well, while transit is an incredibly powerful technique for finding planets, first you have to have a planet that transits. So only about 10% of exoplanets are actually going to have a transit from our perspective. So this is where there's other techniques. So for instance, direct imaging.
But it's not as simple as just taking a picture.
No, I mean, the big issue is stars are very bright and planets are comparatively faint. So you need to go through many steps to block out the starlight before you're going to be able to see faint planets next to a very bright star.
So how does that work? How does this coronography work?
So the simple part is you block out the star.
Okay.
You put a disk over the star. So I can use the demo we used to show transiting planets before, adapt it a little bit to be a coronagraph.
Okay, so instrument construction
real-time
in real time.
Instrument construction.
Nice.
Our star is now a very long distance away from our observer over there. So we just need to line it up in such a way that we block out the starlight, revealing any faint planets orbiting the star.
And there they are, revealed by the coronagraph. Using this method, JWST is already providing images of exoplanets, but they're all very young compared to our own solar system. Why does the age of the planet make a difference?
So a young planet which is just formed is still quite warm, and that means it's glowing a lot brighter than it will at those later ages. And that means that the contrast ratio between the star and that planet is much more favorable compared to if you look at planets like the ones in our solar system, which are very, very cold comparatively and don't put out a lot of their own light. We have to look at them via the light that they reflect from our own sun.
But with the Nancy Grace Roman Space Telescope, scheduled for launch in 2027, we will hopefully be able to see older exoplanets, providing a step towards finding Earth's twin. So what planets will Roman let us see that we can't see today?
Roman will really let us start pushing down to colder planets, older planets, specifically planets that we've likely detected already via other methods.
That'd be cool. So planets that we know are there, but we've never seen, being able to picture them would be fabulous.
Exactly, and that means that we can start studying their atmospheres and really understanding how they work physically.
But these will be the larger outer planets, the equivalent of our own Jupiter. It will take another technological leap before we get to planets like our own. I know all exoplanets are special, but people want to think about Earth-sized planets in Earth-like orbits around Sun-like stars. Is there any prospect of ever getting an image of one of those through this direct imaging technique?
To get to true Earth twins is going to take the next large space telescope, but this is now on the horizon with the Habitable Worlds Observatory.
And this is planned currently for the 2040s, 2050s, right? But people are working on it now. It shows how fast this is moving. We've gone from just having a handful of directly imaging planets to this being really mainstream exoplanet science.
Right now, we're in the golden era of transits, and there's so much being done with that, and thousands of planets detected via transit. But I really think in the next 10 or 20 years, direct imaging is going to catch up, and we're going to have a lot more detections of a lot wider range of planets.
It's exciting stuff. It's amazing what you can do with a coronagraph and the shadows that it causes. Thank you very much.
while the search continues for exoplanets similar to those in our solar system. Pete is looking at our local planets that can be seen in our skies, even when the sun is bright.
When you think about observing the planets, you generally think about looking at them at night. But there are some which can be seen during the day as well. Obviously not today, thanks to the clouds. But if you are going out with a telescope during the day, the first thing to consider is to avoid the sun. You should never look directly at the sun or near the sun unless you're using appropriate certified solar safety filter. The general rule is, if you're unsure about what you're doing, don't do it. This month, Mercury is at a great position to observe during the day, and that's because it has a reasonable distance from the sun's glare, which will allow you to observe it under relative safety. If you are an astronomer with experience of viewing the sun, then it should be possible to view a conjunction or meeting between Mercury and Jupiter, which takes place on the 4th of June. Both planets being at their closest in daylight around 11:30 BST. This will require care to see though, as both objects will only be separated by just over a fist's width at arm's length from the sun. As a consequence, this is only suitable for observing via a camera, and full solar safety procedures are required. So please do be careful and only try this out if you could do so safely. To find Mercury in the daylight sky this month, there are a number of strategies you can use. The easiest method is to get up early and find Mercury in the pre-sunrise dawn sky. If you locate it, center up on it and keep with it after the sun has risen until Mercury is in a higher part of the sky. Another way of doing it is if you've got a go-to mount, which will allow you to synchronize on the sun. So basically what you do for this is you put your solar filter over the front of your telescope to make sure it's protected, and then you remove any finders, etc., which are attached to the telescope for safety. You point the telescope at the sun, and then with the go-to system, you synchronize on that position. Once you've done that, all you have to do is go to Mercury, and it'll find it for you. Couldn't be easier. As well as Mercury, the moon will be visible in the day for much of the month. You'll notice that daylight does have a detrimental effect. It reduces the contrast of the view. Again, if you're using binoculars, please take extra care to make sure you stay well away from the sun. As an astrophotographer, finding the thinnest of lunar crescents in the evening or morning twilight is something which gives me great pleasure because it's actually quite a tricky thing to do. The next new moon will be on the 6th of June, and there are opportunities to capture thin moons on the mornings of the 4th and 5th of June, low above a flat northeast horizon before sunrise, and on the evenings of the 7th and 8th of June, low above a flat northwest horizon following sunset. So do have a go, and if you get any that you're happy with, do upload them to our Sky at Night Flickr, and we'll pick some of our favourites and show them in next month's show. In the meantime, these are some of our favourites of the eclipse that you've been uploading this month.
As far as we know, none of the millions of planets around the millions of stars in the Milky Way have anything as spectacular as a total eclipse. But what is clear is that our exploration has just started, so who knows what we might find. Good night.
On BBC iPlayer now, a three-part series exploring one of space exploration's greatest tragedies, the space shuttle that fell to Earth. For mind-bending conundrums such as, which is best, a bee or a wasp? Listen to The Infinite Monkey Cage, now on Sounds.